Hello, everyone. Welcome back to PyConline AU. You are tuned in to the Science, Data, and Analytics track. I am super excited for the next block of talks that we have for you. And to kick that off, we've got Jakub Nabaglo. Jakub is a machine learning engineer at a four-person startup. He enjoys statistics, musicals, and teaching computer science. We're going to hear him talk about why the float did it NaN. So yeah, take it away, Jakub.
Alrighty. There is a scenario that is all too familiar to many of us. You're training a model. You're watching the loss go down epoch by epoch and by epoch until suddenly NaN. And you know at that point that your training is ruined. Your parameters are garbage and it's a floating disaster. So why does it happen? How can we prevent it? What does NaN even mean? Well, it's all because floating point numbers are an approximation. Example, we're adding 0.1 to 0.2. And we know that in mathematics, it's going to be 0.3. But in floating point arithmetic, it's 0.3 plus a tiny rounding error. That's also why you should never compare floating point numbers just using equality, because it kind of doesn't make sense because they're inexact. So floats are approximations, and we should compare them using approximate methods. But what is the approximation? What does a float look like? Well, you might remember from high school maths scientific notation. So this number is pi to the power of 12, and we can write it down as 9.24 blah 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 times 10 to the power of 5. And floats work roughly like that, except in binary. So forgive the slide. That should be 1.11 not times 2 to the power of 19. And the way this is represented, a 32-bit floating point number, so single precision, has 1 bit for the sign that tells us whether the number is positive or negative. It has the exponent, or 8 bits, so that's the 19. And it has what's called the mantissa. So this is the bit that goes before the multiplication sign. So that's our 1.1100000110. And the digit before the decimal point is always going to be 1, so we can omit it and just put everything that's after the decimal point. There's a few special values as well. So for example, to represent 0, we set all the bits in our float to be 0. If we set the exponent to be all ones, then we represent infinity, and the sign tells us whether it's positive infinity or negative infinity. And to have infinity, our mantissa must be all zeros. And the last special value is when the exponent is all ones, but the mantissa is anything except all zeros. That's our worst enemy, the NaN. Okay, so floats are an approximation, which means that some operations that you do will not be exact. So for example, in this operation, we are subtracting one number from another number, and they're very close to each other. So we get some result out, and because the numbers that we're subtracting were so close together, we don't actually get the full 23 bits of precision. So it kind of appears as if we have an entire floating point number, but we actually don't. Like it's going to be very imprecise, and we don't actually have enough information to fill all the 23 bits. If we're adding one big number to a smaller number, what we will find is the small number will be too small to matter. So for example, if we add 1 to 10 to the power of 16, we'll just get 10 to the power of 16. Another problem is overflows. So if we have the Google, so 1 followed by 100 zeros, if we multiply it by itself, 4 times, that overflows to infinity. It's too big. So the computer just says, look, it's so big, it's practically infinity. And similarly, we can underflow. So if we multiply very small numbers together, what we will find is it will get rounded down to 0. Okay. But so far, this doesn't explain why we get NaN. So we might get infinity, we might get zeros that we don't like, but the NaN, which indicates an error, we can't obtain that yet just with subtraction and addition and multiplication of big or small numbers. Okay. So what happens now when you have operations that don't really make sense? So 1 divided by 0 is infinity, obviously. Minus 1 divided by 0 is infinity, is negative infinity. Infinity divided by infinity, though, is NaN. 0 divided by 0 is NaN. 1 divided by infinity is 0. And 1 divided by negative infinity is negative 0. Now, square root of negative 1 is NaN. You can't do it. The square root of NaN is NaN as well. NaN squared is NaN. So whenever we put NaN into an operation, we should expect a NaN out, like garbage in, garbage out. And NaN to the power of 0 is 1. Okay. So an example of a formula that's very susceptible to floating point errors is this quadratic formula that we are all familiar with from high school. So we have some sort of a quadratic and we want to find its roots. So one example of a quadratic which this formula will have trouble with is one that only has the one root. And the reason why is that the stuff that's inside our square root will be 0. So b squared and 4ac will be very, very close to each other. So potentially we might find that we're trying to take the square root of a negative number and we'll get NaN. And we can expect that just because of rounding errors, if rounding errors cause 4ac to be slightly bigger than b squared. Another scenario where we'll have issues is if one of the roots is close to 0. So in that case, up in the numerator, there's 2 roots. In one, we add negative b and our square root, and in the other one, we subtract. So if the root is 0, we expect the result of that subtraction to be close to 0, which means that it won't be accurate. So there's actually a second version of the quadratic formula which deals with that. So in that case, you would use one version to find one root and one version to find another root much more precisely. So oftentimes we can avoid floating point errors by just doing a little bit of algebra to get a formula that's going to avoid subtracting things that are close to each other. Alrighty. But I want to talk about applications to data science. So one thing that we do a lot in data science is deal with probabilities. So think of, for example, the problem of multiplying probabilities. We have n coins, and we want to find the probability that when we flip those n coins, we'll get n heads. So that's half to the power of n. So we see here that for big values of n, if we try to calculate this, this is very prone to underflow errors, so rounding to 0. Half to the power of 100 is fine. Half to the power of 1,000, that's also fine. Half to the power of 10,000 is too slow to be too small to be represented as a floating point number. So it just gets rounded down to 0. And that's a problem, because you might ask, well, how often do you find yourself multiplying very, very small probabilities? And the answer is all the time. If you're training a machine learning model, usually what you're doing is you're maximizing the probability of seeing the observations that you're seeing in your data set, given the parameters that you're optimizing over. And so that's the probability of observation 1 times, given the parameters, times the probability of observation 2, given whatever parameters, times the probability of observation 3, and so on. So if you have heaps of observations, the probability that you'll get out of this will be very, 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 very small. But you need to be able to represent it in order to maximize it. Okay, but there is a trick. Instead of dealing with probabilities themselves, what we can do is we can deal with the log of a probability. So instead of storing p as a float, we can store log of p. So what does that look like? P is in this range between 0 and 1. The log operation takes that, and it stretches it out, that interval between 0 and 1, to the entire negative side of the real number line. So that means that if we have that entire region of small probabilities near 0, that actually gets stretched out to a very, very wide region of the real number line, which means that we have a lot more space to put in all those very small values. So in our example, if p is half, then log of p is about negative 0.7. And that's how we convert it. Now, logs of probabilities appear often like kind of naturally, if you will. So for example, this formula for entropy is you sum over all the states, the probability of a state times the log probability of a state. The log probability is in a sense like surprise. So there is a reason. So it's not just a cool mathematical trick, but it also has like a nice physical meaning as well. And in this formula, if you have the probability of a state, if you take the log, that's not going to be very accurate. But if you have log of the probability of a state, if you take the exp to get probability of the state, that's a lot more accurate than going the other way around. So storing the log probability instead of a probability is a lot more accurate in this particular case. Now, if you want to multiply two probabilities, that's the same as just adding your two log probabilities. So in our example, we were multiplying probabilities. The log of the probability of having two heads is just the log probability of one head added to the probability of the other heads, which is that. And then the log probability of getting 10,000 heads, which we were unable to do before because we couldn't, because it underflowed to 0. Well, we can compute the log probability of that, and it's about negative 7,000. All right, but what about addition? That's a little bit more complicated because we can't like nicely manipulate the logs to split it like we did with multiplication. Well, okay, so if all we have is log of px, then we can take the exp, and if we only have log of py, then we can take the exp of that. But now we're back to square one because that's just p of x and p of y, and we're back to dealing with raw probabilities instead of their logs. There is a trick we can use to do this accurately, though, and it's called LogAddExp. I will describe it, but don't feel like you need to know it because NumPy implements it for you. Okay, so in this particular trick, what we do is we find the maximum of log of p of x and log of p of y. And we name that a. And we also find the minimum and subtract a from that and call that result b. So the formula that we end up with is the log of p of x plus p of y is 1 plus the log of 1 plus x of b. And that's not obvious, but this formula can actually be evaluated a lot more accurately than if we actually computed P of X and P of Y, added them together and took the log. So this formula is a lot more accurate, and it's not subject to the same underflowing problems, for example. So we can apply it to even very small probabilities. Thankfully, that's implemented for us by NumPy and SciPy. So if you want to add two probabilities together, you can use two log probabilities together. You can use NumPy.LogAddExp. And if you have an array of them, you can do SciPy.special.log_SumExp. So for example, if we have the probability of today being, or tomorrow being rainy as 0.2, and we have the probability of tomorrow as being sunny as 0.3, and we find those log probabilities because we want to store them and compute with them very, very accurately, then we can add those log probabilities together with LogAddExp. We get that particular log probability. And if we take the exp of the log probability to find the probability of it being rainy or sunny, we find that it's 0.5, which is what we're expecting. I am, of course, neglecting the possibility that it might be rainy and sunny at the same time, but I feel it's probably negligible. All right. And the last thing I want to talk about is linear equations, which is another topic that we often deal with in data science. And this is where matrices come in. A matrix is like a grid of numbers. Intuitively, you can think of matrices as perhaps representing your data, but they can also represent transformations. So for example, transformation on a two-dimensional plane are represented by a 2x2 matrix. So a rotational matrix takes some points on a plane and it rotates them around the origin. So that's one kind of transform you can have. Matrices also come in to play when we're solving linear equations. So you might remember and still be scarred by having to solve simultaneous systems of equations back at school. So we have like this entire system of 4 equations, and we want to find x1, x2, x3, x4. Well, we can represent the coefficients of x1, x2, x3, x4 as a matrix A, and we can represent the numbers on the right-hand side as a vector B. And the formula that we're trying to solve is AX equals B, where A is our matrix, X is the vector we're trying to find, and B is the vector that we have. So if A, X, and B were old numbers, what we would simply do is divide the left-hand side and the right-hand side by A. And we can basically do that as well with matrices as well. So we're dividing the left-hand side and the right-hand side, mathematically speaking, by the inverse of A. So the inverse of a matrix is itself a matrix, and whatever the matrix says, the inverse undoes it. So for example, if going back to our transform, we had a rotation transform, the inverse rotates back, and it's also a transform. Linear equations are very, very important. So for example, in linear regression, we have a feature matrix X, we have a label vector Y, and we want to find gradients W. So the formula for W involves solving a system of linear equations. That's where we invert, that's where we compute the matrix inverse of X transpose X. Okay, so how do we solve linear equations? We have a matrix A and a vector B. We want to find X to satisfy AX equals B. Well, one way to do it is we can take A and invert it. So compute A inverse, and that's itself a matrix. And then we can just do matrix vector multiplication to find X. Let's not do that. And use matrix decomposition instead. The reason why that's problematic is A is not always a nice matrix to invert. So in the same way that you can't divide by 0, there are some matrices that you can't divide by, that you can't invert either. So an example of such a matrix is a projection. So we take our entire plane and we squish it into one line. There's no way to figure out where the point originally came from if all you know is its position on that particular line. So you can't invert that transform. But some matrices are technically invertible or mathematically invertible, but they're almost not invertible. So if you find you have a matrix that almost entirely squishes your plane, that matrix won't be very nice to invert on a computer. And so more numerically stable methods will likely do a better job of solving your system of linear equations. So usually what we do in that case is use matrix decomposition methods. So what we do is we find two matrices, S and T, such that A is equal to S multiplied by T, where this multiplication is matrix multiplication. But also S and T are easy to either invert or make it easy for us to solve those systems, simultaneous systems of equations. So that means that we can do step 2 easily. So we can solve X by solving the linear system of linear equations associated with T and the one associated with S. So more concretely, one example is LU decomposition. So we find two matrices, L and U, so that A is the product of L and U. L is lower triangular. That means that all its values that are not 0 are below the diagonal, and U is upper triangular. So all its non-zero values are above the diagonal. And that makes it easy to solve L inverse B. So this is an example of a lower triangular matrix. It has 0 above the diagonal. This is an example of a upper triangular matrix. It has 0 below the diagonal. And the reason why it makes it easy to solve the system of equations is if all the coefficients of X form a lower triangular matrix, then if you look at the equation on the very top, we can easily find X1 by just dividing the right-hand side by 0.73. And then when we go down, we already know X1, so we can find X2 easily in 2 steps, and so on. And it's much easier than if we have a matrix that's full of values. So it makes it very easy for us to find X that satisfies this particular equation. Now, again, NumPy and SciPy implement this for us. So NumPy.linalg has a bunch of linear equation functions that are there for our disposal. The one you probably shouldn't use is SciPy.linalg.inv, because that's the one that inverts a matrix. If you want to use LU decomposition, you can use LU_factor and LU_solve. So factorize your matrix, and solve, actually that's the solving using a factorized matrix. And there's a few other ways of decomposing a matrix that you can use, like QR decomposition or Cholesky decomposition, depending on what else you know about a matrix, but I don't have time to get into those now. And one function that's always very, very handy is simply SciPy.linalg.solve. So instead of inverting a matrix, just ask it to solve it for you. So an example of this is we have a matrix A and vector B, and want to solve AX equals B. And we just plug it into SciPy.linalg.solve, and we get the solution as a 3-vector in this case. All right. So I hope you enjoyed that, and I hope you're looking forward to banishing NaNs for your life, or maybe at least getting a little bit less frustrated when they happen. I await your questions.
My apologies, I was muted. Thank you so much for that, Jacob. That was a wonderful talk. I think you did a great job of explaining some topics very accessibly there. One quick question before we move on to the next session. Do you have any suggestions for people keen to learn more about these topics? Because I think they're sort of things that some people might think are a bit tricky to get into, but I think you've demonstrated that there's some really accessible ways for getting into it.
Yeah, I don't have like specific resources to point you to, unfortunately. I found myself having to learn a bunch about numerical analysis and how to do computations, perform computations in a stable way, just by struggling with errors a bunch for a long time. I'm sure there's an easier way, but I did unfortunately end up learning it the hard way of lots of debugging.
Yeah, I think, having hands-on practice is definitely a great way to go about doing it. And if anyone else has any suggestions for resources, please chuck them in Venulus. And with that, thanks again to Jacob, and we'll now have just a slightly less than 10-minute break, and we'll see you back for the next session on extracting data from Excel in Python.
Thank you, Ned.